Swayam Prabha. Digital India. Educated India.
Good day everyone and welcome to these lectures on physico-chemical processes for wastewater treatment. So, in the last few lectures we have been studying the advanced oxidation processes. So, we have understood that in the advanced oxidation processes various techniques are used for generation of reactive oxidation species. So, these species include hydroxyl radical, various other types of radicals, and which are used further for mineralization of organic contaminants present in the water into CO2, H2O, etc. So, this is done. So, we have already studied the photocatalytic water treatment, wet peroxidation method, the electrochemical treatment of wastewater which included electrocoagulation, electrooxidation and electroflotation. In addition, so we will be continuing further, and today we will be learning regarding another advanced oxidation process which is called as sonolysis. Now, in the sonolysis, sonolysis is like sound. So, we use basically ultrasound for creating cavitation. So, cavitation means creating bubbles. So, this idea is used for generation of reactive oxidation species and which are further used for treatment of the water. Sonolysis can be used individually, also it can be used along with some other advanced oxidation processes including electrochemical treatment and photolysis, where by combining this sonolysis we actually enhance the combined treatment efficiencies. So, we always observe some synergistic effects. So, let us understand the mechanism of sonolysis first. So, in the sonolysis the ultrasound is used for creating cavitation. So, we have ultrasonic waves and this is a wastewater, you can consider that everything is inside this. So, we have a wastewater, and in this case because of cavitation the bubbles are evolved. Now, this bubble will grow, we can see up to a critical size, and as soon as the critical size is reached, that will depend upon the height of water, pressure, all those things as well. So, at the critical size this bubble will collapse, and when it collapses actually inside the bubble the temperature and pressure may be up to this value. So, the temperature may be 5000 Kelvin and pressure may be up to 500 bar within the bubble. So, under that condition when this collapse happens, because of various interaction the reactive oxygen species get generated. So, this generation of reactive oxidation species happens during this sonolysis, and because of which the treatment of water happens. Now, this ultrasonic waves or ultrasound and its frequency that critically affects the generation of these bubbles, and what will be the bubble size, critical bubble size, etc. And what is the duration of duration up to which this collapse happens, after what time, that also depends upon that. So, there are many frequencies. So, up to 20 to 100 megahertz it is kilohertz, it is called low frequency, 100 to 1000 kilohertz it is high frequency, then 1000 to 10,000 we have very high frequency of ultrasound. Now, this particular figure shows the bubble radius we can observe. So, we can see the bubble radius may go up to 200 micrometer or beyond, depending upon the type of or frequency of ultrasound being used, and we can see here the how the bubble growth is happening, and after few microseconds only. So, it is like a blink of an eye, we have the collapse which happens, and as soon as the implosion happens, we have shock waves and rapid quenching that happens, and we have a hot spot created which has a temperature of 5000 Kelvin and 500 bar, and because of this reactive oxygen species are generated. Now, during this process many chemical reactions happen, and because of which these species get generated. So, these chemical reactions are listed here. So, water because of ultrasound may release these radicals. Also oxygen present in the water, nitrogen present in the water, they also generate their respective radicals because of this ultrasound and bubble growth and collapse mechanism. These generated radicals, they further undergo interaction via these reactions which are listed here, and we can see here that we can generate secondary radicals also. Also some of the radicals may combine together to form H2, H2O2, which is not very desirable. Also one radical can get converted into secondary radical, and similarly these radicals may interact with other types of species in the present in the water. So, we have lot of reactive oxygen species which get generated because of the use of sonolysis in the water treatment. The sono-chemical processes is rationalized as a 3 zone system. First is the inner of the bubble, then interface of the cavitation bubble, and then the bulk of the solution. So, these 3 we are more interested in this zone as compared to other. Now, let us further understand the generation of hot spot and the inside of the cavitation bubble and their various reaction zones etc. So, this is shown. So, we have 3 already discussed, we have 3 zones. We have cavity interior. So, it is considered as a volatile hydrophobic substance, the temperature and pressures are already given. So, this is hot bubble reaction is possible where these radicals are getting generated. Then we have a gas liquid interface. So, it is non-volatile hydrophobic substances may be here, and after that we have bulk of solution. So, this is hydrophilic substance, and here all the radicals generated will ultimately go. So, these cavitation bubbles, their zones, these all will depend upon a number of parameters. So, again the same thing is shown here in this particular slide. So, we have cavity interior which is gas phase, okay, the temperature and pressures are very high. Here at the interface the pressure has been reduced, the temperature is still high, and it is where the free radical formation takes place and they react with parent molecules. So, here the thermal decomposition will also happen. Within the hot spot zone we have radical generation certainly happening, then pyrolysis mechanism may also work here, and in the bulk of solution where the temperature is ambient and pressure is also ambient, free radicals they come after and they collide with the parent molecules and their degradation happens. So, this is there. Now, variables which affect the sono-chemical effects. So, there are initial radius of the cavitation bubble. So, what are the parameters which affect this? So, smaller is the bubble size, higher is the cavitation effect. So, this is one thing. So, this is very important. Smaller size bubble can expand higher with more intense than bubble with large radius during the transient collapse. So, this is there. So, the smaller size bubble if it collapses then the effect is different as compared to collapse of large scale large radius bubble, and this is due to higher Laplace pressure in the smaller pressure, that is smaller pressure in the smaller size bubble. Okay, so that is there. The difference between inside and outside pressure of a bubble at the gas liquid interface, which is called as Laplace pressure. So, and this is because of this the effect is different. The critical size up to which the bubble may grow will depend upon the liquid, type of liquid, the frequency of the sound being used, and like for example at 20 kilohertz the size of the bubble may go up to 100 to 170 micrometer. The critical size will depend upon the type of liquid, its hydrophobic, hydrophilic nature, and the frequency of the sound being used. Now, also the presence and the nature of dissolved gases, they also affect the sonolysis process. So, a gas with high specific heat ratio gives a greater cavitation effect than one with low specific heat ratio. So, this is there. Similarly, monoatomic gases such as argon and helium convert more energy upon cavitation than diatomic gases such as nitrogen and oxygen, because of the larger ratios of specific heat. So, within this this is there. Now, gases which are extremely soluble in reaction mixture may reduce the cavitation effect, because the bubbles formed may redissolve before collapse happens. So, this is there. So, extremely soluble gases are will actually hamper the effect of the sonolysis. So, this is there. Now, choice of solvent. So, depending upon what type of solvent or what type of other types of materials which are present in the water, that will also affect the sonolysis. Cavities are more readily formed when using solvents with high vapor pressure, low viscosity and low surface tension. So, if there are organic compounds which are present in the water which have low vapor pressure, low viscosity and low surface tension, then the cavities will be more formed. At very high frequencies, the cavitation effect is reduced, because the refraction cycle of the sound wave produces a negative pressure which is insufficient in its duration or intensity to initiate the cavitation. So, this is the rarefaction cycle of the sound waves that affects the cavitation effect. Similarly, the compression cycle occurs faster than the time required for the micro bubble to collapse. So, sono-chemical reactions are carried out generally in frequencies in this range 20 to 50 kilohertz. So, this is the reason most of the sono-chemical reactions will be carried out under this condition. So, acoustic power also affects the cavitation. So, what is the power delivered to the reaction mixture, that is very important. So, as the power increases, the rate of reaction also increases to a maxima. So, we have to see that we have to use the power in such a manner that the rate of reaction is maximum. If we use the power beyond that value, actually it will not be used. So, our energy consumption will increase. So, we have a critical power that we should analyze beforehand and use in the wastewater treatment using sonolysis. And this critical power is because of the formation of dense cloud of cavitation bubbles near the probe tip, which acts as a block to the energy transmitted from the probe to the fluid at very high power beyond the critical power. So, this is there. Now, there are many types of sono-chemical reactors have been reported in the literature. Some of them are being shown here. So, sono-chemical stir tank reactor, this technology is not much practiced yet in large scale reactors, but these are the different types of reactors which have been reported. So, we can see here this is stir tank reactor, but along with some ultrasonic transducers which are fitted for generating the bubbles and then the using the cavitation effect. So, it is very common steel tank reactor, but it is fitted with ultrasonic transducer. Similarly, this Branson Sono-chemical reactor has been reported. Again we can see the transducers and ultrasonic horn here. The process stream to the water to be treated is coming, and after treatment it is going like this. So, this is again a tubular configuration of Sono-chemical reactor which has been reported. Similarly, a Harwell Sono-chemical reactor has been reported, where the recycling is being done and the water from the steel tank vessel is coming, and then the reaction is being done separately out of the reactor, and here the Sono-chemical reaction mixture. Here this Harwell Sono reactor module has been acted and water is further added and treatment is being done in the usual CSTR method. This is there. Then another Sono tube where transducer is fitted. So, again a simple transducer is being fitted in the line itself. So, here we have inlet process stream and here the outlet process stream is there, where the water is coming out after the treatment. So, these are the various configuration of Sono-chemical reactor. Now, Sono-chemical reactor have few benefits. So, they generally treat the water up to a certain level. They do not have that much capability to overall treat the water fully, remove the COD etc. So, Sono-lysis has been combined with a number of other AOP methods. So, this will be called as hybrid AOP methods. Now, Sono-electrochemical is one such method, and what are the benefits that are being shown here in this slide. So, electrochemical treatment we have already studied in the previous lecture. So, here we will try to understand that if we combine Sono and electro, what are the benefits. So, let us understand or recollect the electrochemical treatment. So, in the electrochemical treatment we understood that depending upon the type of anode or cathode being used. So, if suppose we are using DSA type of electrode, DSA means dimensionally stable electrode. Okay, so, dimensionally stable electrode we are using anode. So, under that condition the anode will be highly stable, not only with respect to anodic oxidation, but also with respect to corrosion. Now, on this surface the pollutants may come and direct oxidation may happen. Similarly, the OH, H2O etc. may go on this surface and these radicals may get formed, and these radicals may react with the pollutants and then mineralize them and convert them into CO2, H2O etc. So, this is there. Now, the problem with electrochemical technology is that after certain time what happens is that a passive layer gets formed on the anode surface. Okay, so, the organics will get attached, but they are not coming out. So, actually the surface which is available for this interaction for direct oxidation or for generation of reactive oxygen species, that decreases, and the resistance in the system increases with time. So, the efficiency of electrochemical treatment method decreases with prolonged use of this particular method. So, what we can do is that we can combine the Sono method along with that. So, if we use Sono-lysis, so it will generate these shock waves during bubble formation and collapse, and because of this bubble formation and collapse, the layer which gets formed, which actually does the passivation of electrode, this layer gets removed. So, layer causing passivation of electrode that gets removed because of this shock waves. So, layer causing passivation of electrode gets removed. So, what happens is that we can do the treatment for longer duration and also the efficiency increases. So, both aspects are there. So, we have a parameter which is called as synergistic effect. So, because of sono-chemical effect, the synergy of treatment increases. So, we will understand this also. So, sono-electrochemical is a combined method of sonolysis and electrochemical treatment. The advantage is that in this in situ cleaning of the electrode surface happens, and this is because of the shock waves. This reduces the electrode passivation problem. So, again efficiency will increase. This also increases the life of electrode. So, there is another benefit because of the use of ultrasound. Ultrasound waves accelerate the diffusion of ions and pollutants because of the increased mass transfer. So, this aspect is also there. Because of ultrasound, the diffusion layer thickness decreases. So, we have overall increase in the mass transfer, and also because now we are using two techniques. We are using sono-chemical sono method along with electrochemical. So, we have more amount of OH radical formation happening, and because of that the overall treatment efficiency increases a lot. Also because of these shock waves, collapse, etc., the agitation, the more amount of agitation is created, and so many times we do not need a separate mixer in the electrochemical treatment. So, sono electrochemical treatment may avoid, with that we may not have to use a separate mixing apparatus. So, in this way we are saving on that. So, overall there are lot of benefits are there with by using sono electrochemical method together. So, that is why these two technologies are being merged together also. Now, within this I discussed about the synergy index. There is one parameter which is called as synergy index. So, suppose we are using sonolysis alone, US alone. So, under that condition, suppose the efficiency is 0.11, we are just assuming, that means or 11% treatment efficiency. Now, if we are using electrochemical method alone and we have suppose 70% efficiency or 70% treatment efficiency. Now, in the synergetic index, what we do is that we try to find out the efficiency when both US and EC are combined together. So, generally we will be finding that this efficiency will be more than the efficiency of both of them combined together. So, it is most likely that this efficiency may go up to 0.95 or 95%. So, the synergy index will be calculated as E US plus EC divided by E US plus E EC. So, that means here it will be 0.95 divided by 0.11 plus 0.7. So, that means the synergy index SI generally has to be greater than 1. So, higher the value better it is, and so this with hybrid AOPs we always look for these parameters to cross check whether they are doing well or not. So, this is there. Now, sonophotolysis is another technique. So, here we can see this treatment is being done in a batch reactor of afloxacin in solution, and we have this, it contains already photocatalysis and UV light is being provided. So, we have photocatalysts which are here, and then the photo oxidation is happening. But if we use ultrasound, so it will increase the efficiency and SI value is likely to be greater than 1. So, this is also possible in sonophotolysis. So, this is how the sonophotolysis works. So, generally it will combine along with the HV. So, we have both light and sound transducers, both are there. So, because of that there is increased formation of radicals, and because of quick formation of radicals we have more treatment which happens, and because of which the treatment efficiency becomes very high. So, this is the sonophotolysis and its mechanism. It is a combination of two advanced processes, mainly sonolysis as well as photolysis. So, we have photolysis happening here, and similarly we have sonolysis which is happening here, and because both are combined together. So, we have enhanced formation of radicals, and which actually oxidize the organic pollutants. So, we have these radicals which are there. So, the photolysis radicals will oxidize the major organic pollutants, other radicals which get generated they oxidize the intermediate compounds, and ultimately we have CO2 and H2O which is getting generated. So, we have increased treatment efficiency because of the combination of sonophotolysis. So, we have till now studied a number of AOPs in this course, and these included photolysis, catalytic wastewater treatment, Fenton process, ozone treatment, then electrochemical treatment we studied in detail. Thereafter, in the today we have studied sonolysis alone and sonolysis in combination with electrochemical treatment and sonolysis in combination with photolysis. So, hybrid AOPs are also becoming very common, and they have lot of potential for use in different industries for wastewater treatment, and in particular in those industries where peculiar type of wastewaters are getting discharged, we have which have some key pollutant parameter which are not common, and these key parameters cannot be treated by the conventional physico-chemical treatment methods. So, then we have to use these AOPs. So, with today's lecture we will end the section on AOPs. We have used a number of references, you can refer to them, and so with that we will end the today's lecture. We will continue with another section on disinfection, and which actually they use the AOP methods only with little bit difference. So, we will continue with the disinfection section from this lecture onwards. So, thank you.